Circular motion 4. A child in a sled slides on a snowy hill. Determine the normal force on the sled when it crests over the top of the hill and also when it is at the next valley. See the figures. Note that the speed is the same in both cases. We've got a child on a sled, and the sled is going over a snowy hill here, and then it's at the bottom of a valley right there. We want to know the normal force on the sled when it crests over the top of the hill. What's the normal force? Very often, when we're asked to find a force, it's probably a good procedure to draw a free body diagram. Let's do that. So there's the child and the sled. The child and the sled together have a mass of 30. We definitely have mg downward. And then what about the normal force on the sled? The normal force is holding the sled up. And because of the curvature of this hill, we know that mg has to be larger than the normal force, because we've said that the acceleration has to be toward the center of the circle. And you see where the tip of my pen is right now? That's where the center would be, right? The center is down here somewhere. The center is not, watch my pen, it's not up here somewhere. The center of the path is down here, which means the acceleration has to be in that direction, and that means that mg must be larger than Fn. Let's do Newton's second law. We've written it 1,000 times. The net force is equal to the mass times the acceleration. The net force is going to be, I always choose positive to be the direction the thing is accelerating. So mg minus Fn, and that's going to equal the mass of the object times the acceleration. In a case of uniform circular motion, that acceleration is always equal to v squared divided by r, which means that the normal force is mg minus mv squared over r. We could factor out an m if we wanted to, but here we have numbers. So let's go ahead and just put the numbers in. M times g is going to be 30, and g is 10. So that's 300. Minus mv squared over r. Maybe I should write that in there. M. And then v squared is going to be 36, because 6 squared is 36, divided by r is 9. So 36 over 9 is 4, so that's 120. So I'm thinking 180. That's the normal force on the sled when we're cresting at the top of the hill. What about when we're at the bottom of the next valley? The speed is the same. The radius of curvature happened to be the same. Now we have to draw a new free body diagram because the old one doesn't apply. We've got mg. I'm going to try and draw mg the same length as I did before. mg. All right, now look at the picture here. Can you see that the normal force is going to point up towards the top of the page? And do you see that that normal force now has to be bigger than mg? Like that, because of the curvature of this valley, the up forces have to be bigger. So let's use Newton's second law. Whatever way it's accelerating, as I said, I choose that to be positive. So this time we're going to go Fn minus mg is equal to the mass times the acceleration. And this is uniform circular motion, so the acceleration is v squared divided by r, which means that the normal force is equal to mv squared over r plus mg. The mass is 30, v squared is 36, r is 9, so that's 120, just like it was, plus 300, which is going to be 420.